penultimate talk session of the symposium. The session is on high-energy phenomena, aka things that go boom. And the first talk today is going to be remote by Ariadna, Murguia, Berthier on accretion onto neutron stars. Go ahead.
Hi, thank you very much. So talking today about disk path accretion onto neutron stars, and I actually only have one introduction slide because I'll be talking mainly about simulations of this very interesting scenario. So it is super common to have accretion onto a neutron star, especially from a disk. I just put here some examples, but there are actually more, but it is a super ubiquitous topic. Now, the problem is that as everything related to a neutron star and accretion in general, doing analytical work is really, really hard because you need general relativity, you need magnetic fields, you need all these things that make life more complicated, but also, of course, more interesting. And the thing is that unlike black holes, neutron stars have a very strong magnetosphere. So you have to add the magnetic fields, which, as everyone knows, just again, make things incredibly more complicated. We need to understand the way in which the magnetosphere affects all this accretion and just like about everything, because the way in which the magnetosphere works and how things get accreted will severely impact the emission of the neutron star. So for example, an isolated pulsar, so an isolated neutron star that's rotating, that has a magnetic field, we just emit in radio, but we wouldn't be able to observe in, say, X-rays. But we actually know some X-ray sources that have accretion onto a neutron star, or that we think have accretion onto a neutron star, like ultraluminous X-ray sources or ULXs. So we need to understand how matter gets accreted onto the neutron star. And we need to understand also just all the accretion, all the radiation mechanisms, everything. But let me just focus on how things get accreted onto the neutron star, because we need to understand that to see if we're actually going to have X-ray emission. So again, studying this effects analytically is quite hard, so we actually need some simulations. But again, there's a lot of challenges because you have strong magnetic fields, you have general relativity, and those two basically just make everything harder. So recently, my collaborator, Carl Parfrey, has simulated the setup with where you have a neutron star with a strong magnetosphere and an accretion disk to study how things get accreted from the accretion disk onto the neutron star. It's a very self-consistent setup. It uses HARM-Pi, which I'm not going to talk a lot about that. I'll just say that it solves the general relativistic magnetohydrodynamical equations. And the setup is very self-consistent. It can take care of the force-free regime where there is a strong magnetic field, and it can also take care of the full magnetohydrodynamical region. So the simulation is, it seems simple enough. You have a neutron star with a dipolar field, and you have an accretion disk. So what's going to happen in that case? So let's take a look at the results. What I'm showing right here we have the neutron star, and here we have the light cylinder. This you can see, so this is the density, this is the poloidal region, this is the equatorial region. You can see the dipolar field here in the blue lines. So this is the magnetic field in that plane. Here I'm showing what's called the co-rotation radius, which is where the Keplerian velocity of the disk equals the neutron star spin, because you have outside here a disk. So I'm going to, this is a movie, so I'm going to play a movie. What happens first is that material will fall from the accretion disk just due to magnetic stresses onto the neutron star. And I'll just play that. And as material gets accreted, the magnetosphere is going to be pushed. It's going to halt the material. And then we're going to have this ring-like structures that are going to then have material be accreted onto the neutron stars, but through these hotspots. So this is very interesting. And let me just talk a little bit about another very interesting thing. So again, material will be incoming to the neutron star. The magnetosphere is going to push the material outside. So we're going to have what's called the magnetospheric radius, which is the radius at which the ramp pressure of the material and the pressure from the magnetosphere will be equal. So it's going to be where the material gets halted. And from the figure, we can more or less see oh, this is the magnetospheric radius. This is where the material is going to be stalled. The magnetospheric radius is an incredibly important quantity. Everyone is trying to get the magnetospheric radius, everyone that does pulsars, because it tells us a lot about accretion. So if it is commonly thought that if the magnetospheric radius is larger than the co-rotation radius, accretion cannot happen because material will actually have to pass through the centrifugal barriers to get accreted onto the neutron star, so it gets quite hard. Whereas if the magnetospheric radius is less than the co-rotation radius, we're going to have accretion, so therefore we're going to have some kind of X-ray emission, for example. We're going to call the propeller regime, it's the no accretion regime, where everything is outside the co-rotation radius, and the other one is reaccretor. So, I mean, that one is pretty self-explanatory. So if the pulsar is in the propeller regime, there is no accretion or almost no accretion, and therefore we have no X-ray emission. Now, the geometry of the magnetic fields is also incredibly important, and of the magnetic fields in the torus is very important. As material pushes through to the magnetosphere of the neutron star, the torus has a magnetic field, and so Carl did some simulations where the magnetic field of the torus was either aligned or misaligned with a dipolar field. And what happens is that if it's aligned, when the dipolar fields of the neutron star encounter the poloidal field of the torus, we won't have any reconnection. It'll actually get pushed away, and it will be something like this case where everything gets pushed away. Whereas if they're anti-parallel, what will happen is that you have magnetic reconnection, and we open up some magnetic field lines. So something like this. In the pulsar case, we have some intrinsic wind. And so if we add more open lines to the normal pulsar, we're actually going to have more pulsar luminosity, and we're also going to have more accretion in these cases. Now, this has been studied by Kyle and Sasha a lot, but they only studied the case where where the dipolar field of the neutron star was aligned with its own rotational axis. But we know that that is not the case for neutron stars. Neutron stars and pulsars have a spin axis that's tilted with respect to the magnetic pole. I mean, that's why we actually see pulsars. There has been even one pulsar where there was a 60-degree misalignment between the spin axis and the magnetic pole. So what happens in those cases for the accretion, that is actually quite interesting, because now, instead of having this ring-like structure, because material won't be able to push in the equatorial region, material will actually, if you tilt it, material from the disk will actually have a preferential, an easier way to get into the neutron star, so the geometry is going to change a lot. Now, doing the simulations is not trivial at all. It seems like, oh, just tilt it, but it's actually quite hard. We need lots of time-dependent boundary conditions. So, I mean, spoiler alert, I'm the one that implemented these conditions. And so I did simulations of accretion onto an oblique pulsar. Again, I should say that this is not at all trivial. It took me months to get the boundary conditions right. So I'm very proud of this work because it was super, super fun to do these boundary conditions. So here, let me show you a movie of what happens. You see the same figures that you saw before. You see the neutron star, the co-rotation radius, the light cylinder. This is the poloidal cut, and this is the equatorial cut. But now you can see that the magnetic field is tilted. So the neutron star is rotating in this axis, but you actually see the tilt. So now material will actually, instead of coming in this direction and being deflected into this ring-like structure, it will come in this direction and just be accreted here. So let me play the movie. Material is coming. And then you're going to see that it kind of gets in these streams right here. And that makes everything way more interesting, because now you don't have a ring, you have the stream. But this stream is actually very low in density, and it's very, very thin. We are still discussing exactly what happens. As you see, this paper is still in prep. We're still trying to figure out exactly why we have a very low density stream instead of more accretion. But the tilting of the neutron star, what we found does is that it decreases the accretion onto the pulsar. So here I'm just showing two different cases. Again, this is the poloidal cut. This is the poloidal cut, and this is the equatorial cut. This is for a simulation where it's basically the neutron star is aligned with the neutron star rotation axis is aligned, and this is where it's tilted. So what ends up happening is that instead of this ring-like structure, we have streams onto the neutron star. But also what happens is that we retain this dipolar field. So in this case, you open up a lot of magnetic flux. but in this case, the lines remain closed. The magnetic field lines remain closed. So there is this two different effects. And in general, all of this results in a decrease in the mass accretion rate, and also very important, an increase in the magnetospheric radius, which means that the halted material is actually, its radius is larger. So in this case, you can even see it by eye that it's outside the corrotation radius, where in here, it's inside the corrotation radius. Which means that if we tilt the neutron star, we get into the propeller regime much more easily, which is something that is very new and very, very interesting and could have some serious implications. So now just for completion, so all of the simulations that I showed have a certain magnetic moment or strength of the magnetic field of the neutron star. But what happens if we change the magnetic moment of the neutron star? So here I'm showing 3 different simulations. This is a lower-ish magnetic moment. This is a strong, medium magnetic moment, and this is a very large magnetic moment or strength of the neutron star field. And this is for a simulation that has a very high obliquity angle between the neutron star rotation spin and the dipolar field. And what happens is that, and this is not surprising at all, if we increase the magnetic field, then the pressure of the magnetosphere increases and the material will feel more pressure. So it's going to be halted. The magnetospheric radius is going to increase and it's going to be halted further apart. Also, the stream you can see, it's a little bit more dense if you have a lower magnetic moment, so you'll have more accretion rate. Thank you. And if we have a very high magnetic moment, basically the accretion disk is blown away because the pressure of the magnetosphere is just too intense. So this is a very propeller regime. This is like a middle propeller regime, or like it's between accretion and not accretion, and this is a full accretor. So let me just summarize what we found. And I know that I'm not going to super explain this figure, but this is like the most important of the paper. Here I'm just showing 3 different quantities. This is the mass accretion rate, the luminosity of the pulsar normalized to the isolated pulsar, and the magnetospheric radius, again, which is where the material from the torus is halted. This is for several magnetic moments and for several configurations of the magnetic field of the torus with respect to the dipolar field. So there's a lot of information in this plot, but let me just go through it. So let's focus on this is as a function of the obliquity angle. So let's focus on when it's aligned. So if we increase the magnetospheric, the magnetic moment, so say like mu of 100, we see that it basically goes to an isolated pulsar. We have no accretion. It's all propeller. That is not surprising. And if not, we get a higher luminosity, or just, and it's quite normal. And it's higher luminosity, and also the magnetospheric radius is inside the corrotation radius. But as we increase the angle, what happens is that, again, the corrotation radius, the magnetospheric radius starts to increase. And you can see it, for example, if we focus on the magnetic moment of 20, we see very clearly that the corrotation radius the magnetospheric radius is increasing, and it actually passes through the corrotation radius. So at some point, at some angle around like 30 degrees, it changes from being inside the corrotation radius to outside. So it changes from being a accretor to being a propeller, which is something quite interesting. Now, of course, there's a lot of caveats, and I'll be happy to talk about those if you ask me. But this is all very interesting results and very new. So we're pretty excited about that. So I'll just leave you with my conclusions that we simulated this fat accretion onto oblique pulsars in 3D, and this is in a very self-consistent setup. And we found that if we increase obliquity, we have accretions through a stream instead of a ring, which is not a new thing, but we found that the magnetospheric radius increases, which is quite interesting. And it is easier for the pulsar to go into the propeller regime. So thank you very much. And if you have any questions, feel free to ask me via the chat, via Slack, or just via email, whatever you want. So thank you.
Thank you, Ariadna. Are there any questions?
This is very super. I was just wondering, are there any interesting feedback effects from the radiation unleashed by accretion, or is it negligible in this problem?
So we didn't do radiation in the simulations. We don't include that. It's just purely general relativistic magnetohydrodynamics. There's no radiation. We're planning on, like, actually with Matthew, who's probably over there, maybe doing something interesting with also adding this, porting this into Hammer, which we could do very interesting things, but as of now, we don't have radiation included. So basically, it's mainly if we have accretion or not, kind of the question.
Hi, I'm Ricky Talk. My question was also about like what are the implications for X-ray or radio?
Over what?
My question
Sorry.
was, what are the implications for radio and or X-ray emission?
Mm-hmm. Yeah, so for X-ray, if we have accretion, we should have some kind of X-rays. What's very interesting is that if you increase your obliquity angle, the mass accretion rate decreases a lot. So you can very clearly see, for example, in the green case, that we have a very much decreased mass accretion rate, which means that if we have a larger obliquity angle, this will probably not emit in the X-rays. It will only emit in the radio.
Okay, let's make Ariadna again.
And yeah, thank you.
All right, we're continuing our Things That Go Boom series with Riccardo Arcodia, who will be talking about X-ray bursts from galactic nuclei.
Can you hear me? From the back. Okay. I'll introduce myself in the meantime. I'm Riccardo, for the ones that I haven't been introduced to. I'm an Einstein Fellow at MIT. I'm going to talk about some niche type of phenomena in the nuclei of galaxies. And you can control that. I don't need to see that. It's fine. Thank you. Yeah. Yes. So I confess that what I do is niche in general for Einstein and Hubble Fellows. So it's not. I need to do an introduction now because there are also Sagan Fellows. So if you have your favorite galaxy out there, and if you want to know whether it's doing something in X-rays, most likely it's not doing much in X-rays, and you won't detect it. But it's studying galactic nuclei in X-ray is pretty convenient if you want to study the coevolution of black holes and galaxies, because effectively, when a black hole is active, its X-ray emission outshines the whole galaxy. So when you see one like X-ray source from a galaxy, in most cases, it's going to be the black hole, the center of the galaxy. So you don't need to worry about pretty much anything. And since the start of X-ray astronomy, we knew that these black holes are variable. Actually, they vary pretty fast, and therefore I think it was one of the first pieces of evidence, indirect evidence, of the existence of black holes in galactic nuclei, because the variability is too fast, so the source has to be very compact in terms of luminosity over radius. So unless we're missing something, it can only be a black hole. But then, so this was the status of things since the 60s until I guess a few years ago. You see a point like X-ray source. Stop and reshare. Oh, okay. Okay, yes. Sorry. Yeah, so this is basically what we've known for decades, right? That the black holes vary, they vary fast, but like they do so in a stochastic way. So no surprises there for several decades. Then some astronomers were looking at this galaxy, a pretty small galaxy, in for a few years. They were looking at it because it was doing interesting things, but nothing, too unpredictable. This is, for example, a light curve from 2014. There's nothing much, like this is a pretty much constant emission in X-rays. And then in 2018, they stared at this same galaxy again, and they saw this sort of behavior. So this is a light curve. This is not a folded profile. So they observe an X-ray burst every few hours from this galaxy, and something that was never seen before. And when you realize that you haven't broken your instrument, so then you try to figure out what it is. And they gave this phenomenon this name, quasi-periodic eruptions. Now we have to stick by it. I guess it's what it is. And I think this is still pretty niche for the community. Maybe some X-ray people know it. I guess most of you never heard about these things. Am I right? And you shouldn't feel too bad, because I asked ChatGPT what QPs are. And apart from, you have to be nice to ChatGPT because you never know in the future. But then I asked what QPs are. And then, sure, it finds something about astrophysics, but then it goes on about geological, biological systems. And then at this point, I don't even want to know what QP is in a biological system. Maybe after the conference dinner. But anyway, so you shouldn't feel too bad. It means that there just isn't enough data on these sort of sources, even in the internet. So it's something very new. If we do a fast forward 4 years, we only know a handful of these sources. After the first was found, you can see it in the top left here. The same group went back on the archives and found another one. That was pretty much it for a while. And then there are 4 more now. I found 2 a couple of years ago, which are public. There are 2 more coming. I'm almost submitting this paper, but that gives you an idea. You see the properties are, that they deserve the quasi in the name. They're not exactly periodic, but we don't know many of these sources. They're just 6. And I guess there are hundreds of thousands of extragalactic X-ray sources in the archives. They're hard to find, but I'm going to convince you that they're pretty interesting. Now, there are so many reasons why they are interesting for X-ray astronomers, and it's just going to be maybe 30 seconds of information here. So the overall recurrence is a few hours. So they repeat. These galaxies have a nucleus that goes in outbursts in X-rays. These outbursts last an hour to a couple of hours, and it repeats every few hours. And these are timescales which are very unusual for galactic nuclei. Usually, to accrete some gas, viscous timescales, these timescales are 100,000 times longer, tens of thousands times longer. And so this is something else, obviously. As of the lifetime, so the ones that we've discovered are still emitting this sort of burst. So what we know is that they do so for at least a few years. In particular, this source had an archival burst in the year 2000, so it could be a few decades. Still something very small for a galactic nucleus, but it's convenient for us. I mean, if the TAC panels don't give us data, we can try the next year, and it's probably fine. I shouldn't tell you this actually, because we'd never give me time. Well, this works if they're not stopping, and they might stop. So give me time this year. But just to give you an idea as to why they have to be nuclear, the peak X-ray emission can reach 10 to the 43 ergs per second. Pretty much nothing else can do it. So even if we don't have a sub-arc second positional accuracy for all of these sources, they are from the nucleus. We know this. And it's pretty interesting that they don't do much in other wavelengths. So they don't have any counterpart, in the sense that, so the caveat is that in the rest of the SED, the galaxy is probably dominating the emission. So with the current instruments, we didn't find anything, but we have ongoing programs to try and isolate the galaxy and just look at the nucleus. We'll try again, for instance, with HST, fast photometry. But so far, what we know of is that they only do funky stuff in X-rays. But I want to convince you that they're actually interesting for the generic crowd of astronomers, rather than getting into more details. And it's because these QPs are found in low mass galaxies. Now, this is a plot in which there is a number density as a function of the mass of the galaxy stars. And they didn't add the gray area here. People that do population studies get rid of the low mass galaxies because it's hard to find them. Samples are incomplete. And also, we have a pretty clear understanding of the coevolution of black hole and galaxies at the high mass end. We know that every massive galaxy has a black hole of about 1/500th of the mass of the galaxy in stars. But we don't even know if at the low mass end, all the galaxies have a black hole altogether in the first place. In fact, this is quite important for seeding models, for the high-redshift seeding models, because the local universe should be a good tool to test the seeding models, but it's hard to find these galaxies in the first place. It's hard to figure out whether there's a black hole in this galaxy. Now, I'm not saying QPs are going to solve this problem because it's just too few numbers, but these galaxies are exactly here at this turning point. So we are actually scratching the low mass end of the black hole galaxy coevolution. You can see on the left here that the relation between the black hole mass and the stellar mass of the galaxy, QPs lie exactly when there are many points, which is important in the sense that X-ray transients in general, TDs, and tidal disruption events as well, are giving us a way to find that in these most small galaxies there is a black hole pretty easily and obviously. And I think the lowest mass of my QP sample, our QP sample, is 10 to the 5. So it's a black hole of 10 to the 5 in a small galaxy, which, of course, it's with the usual tax of uncertainty, but that can go both ways. It means that we are scratching the intermediate mass black hole regime. So maybe with future telescopes, we will actually find some. Another reason why they are interesting for the generic crowd, so is that the leading model, there are several interpretations, and to be clear, none of them has tested quantitatively against the data, right? So there are more ideas out there, but like scientists are focusing on this scenario at the moment. There were a few papers in spring in which basically long story short, if you have this sort of binary with an extreme mass ratio, the setup is that there is a massive black hole at the center of this galaxy with its accretion flow. There's a stellar mass orbiter in an elliptical orbit, which is dominated by gravitational wave energy loss. So this system, in principle, could last many, like 10 to the 5 to the 6 cycles. Statistically, it should be able to do so. And what models are doing, long story short, is that they are finding a mechanism to trigger bursts at each pericenter passage. Now, without going into many details, because to be fair, most of these models have different prescription for the physics of the burst and exactly what is making the eruptions. It's not worth it to get into details now. But the whole point is that if this is the correct scenario, it's going to be pretty fundamental in the future because these MRIs, extreme mass transmission spirals, are detected by LISA. Not all of them, only the black hole MRIs. And we don't know whether QPs are MRIs in the first place, but if they are, if it's a star or a black hole. So, this kind of changes a bit whether we will be able to use them for multi-messenger or not. But regardless, even if the same source won't be used for multi-messenger astronomy, if QPs are MRIs, what I can do observationally, since, I didn't explain it too much. I'm finding QPs with one telescope with an homogeneous survey, so I can actually give you the intrinsic rates of these sources based on the SIR one. Now, at the very least, if QPs are MRIs, of course, the intrinsic volumetric rates of QPs is a lower limit to the MRI rates. And to my knowledge, no other type of observation have done that in the past. So the MRI rate comes only from theory at the moment, and it's very, very uncertain. So this is just a plot, just focus on the green points. It's a number density as a function of extra luminosity. Now, if you just focus on the right-hand y-axis, I converted the volume in number of galaxies, assuming that these galaxies, like the observed one, are about 10 to the 9, 10 to the 10 in stellar mass. What I can give you from observations is that there is a given number of events at any time per megaparsec cube. You assume some galaxy density, and what you find is that there is one galaxy every 10 to the 4, which is emitting QPs at any time. Why at any time, not a formation rate? Because they last for years or decades, so they outlive your survey. So you don't have a formation rate, you just have like an abundance rate, how many there are in the sky at any time. If you want a formation rate, which is, I guess, useful for the LISA people, you have to assume the lifetime, which we don't know. Let's say 100 years from now, just for an example. It means that every galaxy and every 10 to the 6 years or 10 to the 7, if you assume 1,000 years, starts this QP behavior. So this is, to my knowledge, something that was never done before. And it's early days because we still don't know for sure whether QPs are MRIs, but just this gives you an idea how powerful these sources could be for the future. I'm just I think I have a minute, so I'll just guide you through the summary. QPs are a new exciting phenomenon of black hole accretion on massive black holes. There are these crazy repeating extra flares from galactic nuclei. There are only a handful so far, and the team I led found 4 of these 6. And this is because effectively you need all sky monitors and X-rays, and there aren't many at the moment. But we'll try with future probes to figure out whether we can find a discovery machine for these sources. The scenario under investigation is currently that of an extreme mass ratio spiral, but there are other options, and these have been only qualitative tests so far, but the community is excited because this will open a lot of interesting things for the future of multi-messenger astronomy. And with this, I thank you for your attention.
Right, are there questions for Riccardo?
Thanks, Riccardo, that was great. I was wondering, do you get enough counts to look at the spectra? Can you get a spectrum in the outburst? I'm not sorry if I missed the.
Oh, no, I didn't show it. So whoops, what did I do?
So I just wondered if you notice any noticeable change between this outburst spectral.
Yes, that's a good question. So it is a question from exosomes. So I left it out for the slides, but basically if you take the spectrum when the source isn't in outburst, so the one in red, it's an ultra soft spectrum, so very unusual for galactic nuclei, which usually have an outer power. And you can interpret these like as you do in TDs as the entail of the accretion flow around these 10⁶ or mass black holes. But also the spectrum in outburst, you can just look at the blue one here. It's still very soft. Now, what people interpret as in the Emery scenario, it's either an accretion burst from partial disruption or shocks. So the gas temperature is somewhat proportional to the temperature here. So it still is a thermal distribution. Yeah, this is it. There is basically there's hardly any count above 1 or 2 kV. And it might be because of sensitivity. You know, if there is a ratio, volumetric ratio of 100, like in AGN, you wouldn't actually observe this power law. So we don't know yet.
Cool. Thanks.
Another question? Are there?
Do you know if any of the systems that you detected would be observable by some use?
So there were 2 papers. One was saying yes, one was saying no. But like I think the problem is that you have to assume an orbital system, specific orbital system, you know, all the distances in centimeters and all that. And I think it's hard to do at this stage. There are a lot of degeneracies, even in Emery models, you know, people that say it's a partial disruption, then everything happens at the tidal radius. People that say it's a collision with the star and the flow, it can be arbitrarily from the tidal radius outwards. So, and you change those parameters and you change the detectability. So it's early days.
All right, let's thank Riccardo again. All right, our next speaker in the Think That Go Boom is Lea Marcotulli, who will be talking about the most powerful persistent jets through cosmic times. Can you guys hear me okay?
All right, thank you very much. So hi everyone, I am Lea Marcotulli and I'm starting my 3rd year as an Einstein Fellow at Yale University, and I'm really happy today to tell you about some of the work that I've done.
The sharing, so.
Sure, but it's not actually shared.
Yeah.
I think she shared her desktop. So yes, some of the work that I've done quite recently, actually, because I started thinking what was an audience that doesn't really work with powerful jets care about. So I hope that in the next few slides, I will tell you a few things about laser jets, hopefully convincing you that they're really, really cool, as an undergraduate that I work with once said, but also that we need a new X-ray telescope. So if any of your sources emits an X-rays, just let's talk later about this proposed mission. So first of all, because some of you may have never really studied these kind of sources, I work with blazars. So blazars are active galactic nuclei, like Riccardo was saying, but they power strong jets that point very close to our line of sight, within 5 to 10 degrees from Earth. Peculiarly, their spectral energy distribution shows this kind of shape. So right here, you see an SEDs of several blazar sources, so luminosity versus rest frequency plot. And you see that it extends from radio all the way up to gamma rays. So these sources have been grouped in gamma ray luminosities, and you see that their spectral energy distribution shows these two broad peaks, one peaking at lower energies and one at higher energies. And what you can also see by eye is that as the source luminosity increases, both of these peaks shift to lower frequencies, to a point where actually the most luminous of these sources have their high energy peaking in the MEV band, and they can reach bolometric luminosities of 10 to the 48 and 10 to the 49 per second. So those are some of the most powerful persistent objects that we know of in the universe. These guys, also known as MEV blazars for obvious reasons, are so powerful that we find them very early on in the history of the universe, beyond redshift 3 up to redshift 5 or even 6. So this is a time when the universe was barely 1 to 2 billion years old. Here you see a significance map of one of the farthest gamma ray detected blazars that we know of. So really powerful, really early on. And apparently, as we start finding more and more sources at high redshift, we actually started noticing that the higher the redshift, the more massive the black holes that they host. Here in this histogram, you see a histogram of black hole masses of blazars detected below redshift 3 in blue and above redshift 3 in red. And as you can see, the histogram of red sources are peaked to higher black hole masses. So now, as we find more and more of these black holes and their jets earlier on, the question comes, how did these black holes grow so big in such short time scales? And you can think of these questions also by looking at the supermassive black hole space density plot shown here from the work of Sbarrato et al. In 2015, where the authors saw that there was a dichotomy between radio quiet and radio loud AGN. So here you see supermassive black hole space density on the Y as function of redshift. Radio quiet sources are those AGNs that don't have strong radio emission, so don't have radio jets, and their black hole space density peaks around redshift 2, the so-called cosmic noon, where most objects that we know of the universe peaks in evolution. While if we look at the radio loud sources, so those black holes that have jets, we see that they're traced by the orange line here, and they're traced by studies of blazar sources. It actually peaks quite earlier on at a redshift of about 4. So this means that there is a strong connection between fast black hole growth and the presence of a jet. But of course, this kind of sources strongly relies on the number of sources you find per redshift bin, and how well do you constrain their evolution through time? Because these kind of plots strongly rely on luminosity function of blazars that tell us how did this source evolve through time and luminosity. So when were these slides downloaded? This morning, okay. Do you mind if I go to the Google Slides? Because I may have modified a few slides. Here, let me go. Slideshow. Okay. So all of this, just, you know, all of this now? So why do we care about blazars? Because for every blazar you detect, you're really lucky. You're really looking down the barrel of jets. And for every source that you find with disorientation, you can actually infer the size of the parent population. So all these jets at the same redshift with the same black hole mass, but pointed somewhere else. And this is called the 2 gamma square correction. Gamma is a factor of the jet, the ball tolerance factor that tells you how fast are these electrons moving. Sure. Absolutely. So share, start my video. Okay. Is it good? Perfect. So yes, if you have the gamma factor that usually is about 10 to 15, you can think that for one source you detect, you imply the existence of 200 to 400 such sources. So this is why we use blazars for this kind of studies. And in terms of their evolution, I actually redid the X-ray luminosity function and confirmed that the peak of the evolution is beyond redshift 4. Okay, so this is the most up-to-date X-ray luminosity function of blazars as function of redshift to the left, luminosity to the right. And here, this representation is not great to see the turnover here, but the best fit model shows that the peak of the evolution is beyond redshift 4. However, if we look at the luminosity plot to the right, you see that no matter the redshift bin we're looking at, we are sampling a power law shape. Because it's a power law, we don't really know what kind of evolution is happening to these sources. Are they more numerous at earlier times? Are they more luminous at earlier times? we still cannot tell them apart. So we really need a deeper X-ray instrument to tell these two scenarios apart. So they peak at redshift 4, let's go find them, right? So how do you find blazars beyond redshift 4? Unfortunately, gamma ray instruments are starting to not be able to detect these sources for sensitivities, and the fact that the peak just shifts to lower and lower energy, so they are not bright anymore at gamma rays. So you back for time with X-ray telescopes, specifically the NuSTAR one up here, that's hard X-ray telescope. And we got time to observe 10 such sources at redshift beyond 4. And then we trigger a multi-wavelength campaign with soft X-ray instrument, optical instrument, infrared, whatever we can find. But at high redshifts comes the price of very faint sources, because of course you ask for the minimum detectable time. And so you see here, this is a high redshift source, and you see doing NuSTAR, so hard X-rays. You see the background is almost at the level of the source. So right now what I'm working on is try to understand how this background is affecting our observations. And another thing that, if you've heard of blazars, something about them is the fact that they are multi-messenger emitters, not just multi-wavelength. Actually, we had TSXO 506 was the first blazars detected in coincidence with a neutrino event. So if you have neutrinos, you probably have protons that contribute to the emission in these jets, right? However, most models that explain jet emission from these blazars use the Skull leptonic model, where electrons make up for most of the emission that we see, while some people have started working on hadronic modeling, so protons are major contributors. And here you see a blazar studied by Butcher et al. In 2013, to the top with a leptonic model, to the bottom with a hadronic one. Who in this room can tell me which one is the best model? I don't think you can. I can't. And also I would like to point out that we have a huge gap in wavelengths that is from basically all the hard X-rays up to the NEV range that we need to fill to understand where you see the models predict different shapes of the SED. So with this in mind, here is another blazar SED. This is actually the TSXO 506, the neutrino emitter. This was studied in, so people found a neutrino coincident with this blazar source, and they went back into the neutrino data and tried to, they found that there was a flare in 2014 where this source was coincident with a neutrino event. Okay, so this is neutrino emission right here. This is all the very well sampled multi-wavelength SED of the source. And you see that these different models predict the different shape, and a very important energy range that we would like to sample to understand what's going on in this source is the middle part right here. And so for this sampling, what we would need is actually an X-ray instrument that has a broadband coverage. So I was lucky to be invited to be part of the HEXP collaboration. So HEXP is a newly proposed X-ray mission. As you have heard on Monday, NASA has strongly, after the astrodecadal survey, they strongly pushed either for X-ray or infrared instruments. And I'm part of one of the instrument that will be proposed. And I was leading the blazar team. So we were trying to make a case with blazars for this mission to be launched. So now I will convince you why this instrument is great for our studies. But again, if your sources emit X-rays, think about this instrument. A few technical details. HEXP will cover simultaneously from 0.2 to 80 keV, almost 2 orders of magnitude in one go. Energy resolutions you see right here. Sensitivities of megasecond surveys show that we're going to do better than current, mostly hard X-ray instruments. High time resolution, very good PSS, both as soft X-rays and hard X-rays. And those are field of use comparable to what NuSTAR has, for example. But leave the details aside, you can find it in the slides. What can it do for blazars? Well, first of all, I told you right now, we don't know what kind of evolution is happening to the most powerful of these sources. And these kind of instruments would be able to tell the two apart, because if you see here to the right, this is number of sources detected per redshift in a density evolution scenario in bluish and luminosity evolution in pink. And you see the two are quite different from each other. So HEXP would be able to see more sources or more luminous one as we go further on. Moreover, because of the time sensitivity, the time resolution, both as soft and hard X-rays, we will be able to have an extremely well sampled light curves simultaneously, like at the same time. No need to beg for all the X-ray instruments that you can think of, from 0.4 kV to 20 kV. This was a simulation with a laser magnetic reconnection scenario where we could literally tell if this is happening in our laser jets. And also, this was one of the results that we got out of this laser. I don't know how good the resolution is, but this is the Chandra image of a famous radio galaxy. This is not a laser. This is NA seen in soft X-rays by Chandra. Beautiful image. What does it look like in Nooster? Beautiful image, isn't it? It's a blob. We don't really know what's happening. We can get some estimate of the flux, mostly from the nucleus. But if we had an instrument such as HEXP, this is what we would be able to see. The resolution in hard X-ray would be for the first time, and you guys don't see much, but go see the slides online when you have time. We will be able to distinguish the nucleus, the jets, and all the point sources around it. This and much more of laser science with HEXP will be published soon. A lot of different teams are working on different subjects. We're also making papers for actual publication. It's not just white papers. And with this, I also would like to thank the team. These are international collaboration with some people in Europe, some people in the US, and both Murguia and I were leading this beautiful group of people. So yes, I'll leave you here with some these are just like a few other things that I worked on. If you have questions, ask me. Otherwise, I'm happy to take questions. Thank you very much.
Any questions for Lea?
Thank you, very interesting talk. Regarding the source where you have that neutrino detection, is it one of these MEV sources or the more harder high energy sources?
Those are the ones that actually, this is not an MEV source. I don't know if this SCD will show it.
And the neutrino detection was by IceCube?
Yes, that was neutrino detection by IceCube, yes.
You said that there's a coincidence between the jets and the neutrino emission.
Yes.
But what is, do you know what was the spatial coincidence? Like how?
So, yeah, it was very difficult to associate, and the association is at a level of 3 sigma, so it's not super, like some people don't believe it, let's say, but, and also because many people have tried to model these laser jets with the neutrino emission, and not many models can reproduce the neutrino emission. But no, this source is not an MEV laser at all. It's actually one of the sources that peak at higher frequencies, and people have thought that is a very so they're trying to understand whether it's more of an electronic or a hadronic emission and whether you can reproduce the neutrino flux. But yeah, we don't really know the answer to that right now.
Great talk and exciting possible mission. I'm curious on how well you're able to account for the fact that when you're looking back at high redshifts, you're biased towards more luminous objects, and therefore they're likely more massive too. And so how much uncertainty might there be on certain two different distributions in the fact that there might be this bias that's built in?
That is a really good question. So what we're trying to do, it is true that as you go to higher redshifts, you're gonna be more likely finding more bright sources and more luminous sources, sorry. And the fact that we do still see these massive black holes means they exist. So actually those supermassive black hole space density are still correct in the sense that those black holes are there in these kind of sources. There could be fainter and so less massive black holes, like we are not able to detect them, but that wouldn't change the results in the plot that I showed you. What can actually change strongly the result is if we look at these sources and we measure the black hole masses, are all these sources with this high black hole mass? And the answer starts to seem yes. Actually, all the sources that we look at those redshifts has these black holes. The gamma factor, however, is a bit uncertain because gamma, it seems to be a bit lower than people usually predict. So actually the number density could come down because of gamma factors more than black hole masses.
Okay, let's thank Lea again. All right, next thing that go boom. The next talk is by Elias Aydi on exploring the formation and characteristics of shocks in novae.
Quick question, does anyone have a laser pointer by any chance? Tim, thank you so much. Just a pointer, no need for. Sure. I'll speak loud. I'm very loud. Put it down.
It is much
Yeah,
better.
okay, that's good. No. Is that sharing? No?
It's. Yeah, we just share the specific window. There we go.
Yeah, why don't you turn the mic around?
That's, can you hear me at the back? Awesome. We good? Cool. Hi, everyone. I'd like to thank the organizing committee and the leads for organizing this symposium. My name is Elias Aydi. I'm a Hubble Fellow at Michigan State University. And today I'll be talking about exploring the formation and characteristics of shocks in novae. This work is by no means solo work and is done with a long list of collaborators. So starting with a brief introduction, novae are stellar eruptions which occur on the surface of white dwarfs and cataclysmic variable systems. So I have white dwarf accreting material from rush law filling companion via an accretion disk. The material builds up on the surface of the white dwarf, increasing pressure and density. And at a certain critical point, a thermonuclear runaway is triggered, which eventually leads to ejecting at least parts of the accreted envelope with velocities ranging between a few hundred and a few thousand kilometers per second. Emission from remnant nuclear burning on the white dwarf surface diffuse through the ejecta and peak initially in the optical and then the ultraviolet. And as the ejecta expand, they become more transparent to the nuclear burning on the surface of the white dwarf, which peaks in the super soft X-rays. So if you look at the SED of a nova, it initially peaks in the optical, then the ultraviolet, then the super soft X-rays as the ejecta expand and become more transparent to the central emitting source. After the party is over, the accretion resumes on the surface of the white dwarf, building up for the following eruption. So in a nutshell, novae accrete, erupt, and then repeat. Based on this picture, one would expect the optical light curve of a nova, a typical one, would show a quick rise to a peak followed by smooth decline as the SED emissions shift to higher energies. But novae do not like to behave, and you see diversity of light curves from long-lasting peaks to jitters and flares, oscillations, and only small fractions of novae show well-behaved smooth decline. And Schack's reaction here is actually all of us in the field when we look at light curves like this. So to summarize, novae, as we know them, are stellar eruption, which luminosity is powered by thermal emission from a hot white dwarf. But this picture has been challenged with a shocking discovery by the Fermi Large Area Telescope, which started detecting GeV, gamma ray emission from several galactic novae. And I said a shocking discovery because literally you need shocks to accelerate particles to relativistic speeds, so they emit gamma rays. I do not have time to go through the calculations, so you have to trust my words for it. But given how bright the gamma ray luminosity of nova is, we expect that these shocks are very energetically important and they could radiate a large fraction of the visible luminosity of the nova. So basically, we know that the shock energy, only a smaller fraction of it is used to emit gamma rays, while the vast majority of the shock power will heat up the gas to X-ray temperatures, where this X-ray is radiated, reprocessed by the dense ejecta ahead of the shock, and where it escapes in the opticals. So we have an additional source contributing visible emission to the nova in addition to the white dwarf surface. Now, of course, if you don't want to trust me, bro, you can check all these studies where we detail these calculations. Now, this theory or this suggestion got some observational support with a nova from 2016, which optical light curve in blue here and gamma ray light curve in black showed the same trend, which should not be the case unless the gamma ray and optical are coming from the same source. And we know the gamma ray is coming from the shock. So it's very likely that a large fraction of the optical is also coming from the shock. But the smoking gun evidence came with this nova from 2018, where we see flaring activity happening both in the optical and the gamma ray at the same time. And the fact that this is happening simultaneously in both bands means that they very likely share the same origin. And we know the gamma ray is coming from the shocks, so the optical should be coming from the shocks. And given that the luminosity of the nova doubled during these flares means that the shocks could indeed radiate a large fraction of the nova luminosity. In addition to that, now we have some answers to some of the flaring or like weird features we see in nova light curves, which could indeed be coming from shock interactions. So finally, Shaq got some answers. Now, this new insight into novae and brought by Fermi and given how bright novae are in gamma ray and how common and nearby they are, we can use them as ideal laboratories to study more distant, less frequent shock-powered transients such as supernovae, type 2n supernovae, or fast blue optical transients, whose visible emission cannot be explained solely by decay of radioactive decay of unstable elements, and shocks has been theorized to contribute to their optical emission. So we are working actively to understand how shocks work or form in novae. And I'm sure many of you have already assumed that when I'm talking about shocks in novae, these shocks should be happening between the nova ejecta and some circumstellar material or circumbinary material, which could be the case when the secondary star is a giant evolved companion, which is enriching the circumbinary medium with a lot of material. However, most of novae discovered by Fermi or detected by Fermi have a main sequence companion with low density circumbinary media. So our prediction is that these shocks are internal to nova ejecta, more precisely happening between two phases of mass loss. An initial slow dense ejection, possibly directed in the equatorial direction by the binary motion, followed by faster wind, which slams into the earlier slower flow, creating the gamma ray emitting shocks. This was first based on the radio interferometry of a nova from 2012, which the color images here are actually thermal radio emission, while the black contours are synchrotron emission. And initially, we cannot resolve the nova ejecta early on, of course, but then we start seeing two blobs moving in this direction. And we think this is the earlier bipolar flow that is much faster, and we can resolve it first. And then 2 years later, this flow has dissipated, and now we start to resolve the early slow flow, where we see these two blobs moving in the perpendicular direction to the earlier blobs. Another evidence for this two-odd flow scenario came from high-resolution optical spectroscopy, where if we follow a nova with dedicated high-resolution spectroscopy as it's rising to peak, we see this low velocity P Cygni profiles with velocities of a few hundred kilometers per second. And then at peak, suddenly we see a broader emission emerging with velocities of a few thousand kilometers per second, while the P Cygni profile is superimposed on top of it. This indicates to us that there are two physically distinct injections with very distinct velocities, with the fast one blowing from the inside of the slow one. We see this in all novae that we manage to get spectra for as they rise to peak and then they decline. Here's some example from a paper from 2020. Each one of these is a different nova we observed before peak and after peak, and we see the same evolution and indication for the presence of two R flows. But of course, slam dunk evidence would come from actual imaging that could follow up the nova from the early days all the way to years into the outburst. We know we can do this with facilities like JWST and HST, and of course, months or years into the outburst, we can easily resolve the ejecta with facilities like the VLA. But during the early days of the outburst, is it possible to resolve the ejecta with imaging? Well, it wasn't until we had Chara. Chara is a near-infrared interferometer, and it can do really cool stuff, and I'm going to show you some example. Starting with a nova from 2021 called V1674Her, a very fast nova, rapidly evolving, smooth light curve, and we managed to get two Chara epochs during the second and third day into the eruption. And this is what we got. We see just 2 days into the eruption, some signature of asymmetry with likely the presence of two R flow. One that is expanding in this direction at a greater rate, and another one, central one, moving at a perpendicular direction at slower rate. This is huge, Remember that usually looking at two novae at a nova 2 days into the outburst, this is how they look like usually. And now we have this. So this is mind-blowing, at least for me. Now, when we look at the spectra taken at the same time, we see these Cygni profiles with really high velocity in this one because it's a fast nova, 3,800 km per second. And then we have another component emerging at 5,000 km per second. And if we use this velocity and how much this outflow has expanded during 1 day, and we derive the expansion parallax, we get the distance to the nova of 6 kiloparsec, which is the exact distance to the nova derived from other matters, meaning that what we are seeing here is very likely real. Now, the other example, the final example, is of a completely opposite nova, a very slow one, lasting in peak for around 200 days and showing these flaring activities and jitters. And this is a zoom in on the first 100 days where we have these big flares here. We got 3 Chara epochs. Between them, the nova was detected by Fermi. And one explanation for why novae stay in visible peak for so long is that for some novae, the envelope might not reach escape velocity immediately. So the white dwarf envelope puff up, it engulfs this system, and then due to the momentum from the binary motion in a common envelope scenario, the envelope eventually get enough momentum to be expelled. And when we look at the Chara images in this nova, 50 days into the outburst, and there is still no ejecta around the system. So it's very likely that here we have a puffed up envelope that is not ejected. Then later on, we start seeing some structures, and 2 weeks after this first epoch, we start seeing more structure. And if we compare this to the spectra, again, initially we have these Cygni profiles, and then when the nova start declining from this flare, we see this 2100 km per second component much faster. And if we derive how much this component, this structure here has expanded, using the 2100 km per second velocity, we get the distance to the nova of 1.8 kiloparsec, which is the Gaia distance to the nova. So again, what we're seeing here is very much real. And also, this provides us a good evidence that novae that stay at peak for so long could eventually be due to the envelope not being ejected and having some sort of a common envelope phase, giving us some more answers about why some novae show these very weird features, and of course, Shack is even more ecstatic. So this all means that novae could be miniature common envelope event, evolving in real time in front of us, unlike, for example, planetary nebulae, which takes thousands of years to evolve. And now we have the perfect set of instruments to actually track the evolution of the ejecta across different stages of the outburst, so allowing us to better understand or constrain common envelope physics in these very valuable laboratory in our galactic backyard. So before I leave you with my summary, I would like to highlight 2 projects that also I've been busy working on in the past few months. Unfortunately, I didn't have enough time to talk about them, but I recommend you to check them. And if you have any questions, please send me on Slack. And now I can leave you with my summary. Thank you.
Thank you, very nice talk. In one of the first slides, you said that these novae have quite a wide range of gamma ray luminosities. Do you know the answer? Why?
Sure. So this is actually a very interesting question, and we've been trying to answer that. So when you look at novae, they could be like, and the gamma rays 10 to the power 35 ergs per second, all the way to 10 to the power 37 ergs per second. So what is causing this wide range of gamma ray luminosity? Actually, I have some slide that I did not show. So one of my students, Ashley Stone, is working on a project to try to determine what causes this wide range of gamma ray luminosity or even duration. Some novae emit gamma rays for a couple of days, some of them emit gamma rays for 2 months. So why this range of velocities? So we know that the shock, we know that the shock luminosity should be mostly determined by the density of the interacting ejecta and their velocities. And since we have high resolution electrical spectroscopy that would allow us to measure the velocity of each of these 2 interacting ejecta, we can see if there's any correlation between the gamma ray luminosity and the difference between the velocities of these two ejecta. And actually found a really nice correlation where we can see that indeed the higher the difference in the velocities between the two outer flows, the stronger the shocks are and the more luminous the gamma ray emission is. So yeah, this paper, I didn't want to spoil it, should be out on archive very soon. So let's stay tuned.
Another question?
Yeah, very nice talk. So I was wondering, so in the common envelope scenario, you would expect that, especially if the companion mass is low enough, that there would be some failed ejections where the envelope shouldn't get ejected. What do you reckon the nova looks like in those cases?
So there are some simulations of failed eject nova, and they have a very, I would say, narrow initial conditions or parameter space to get these failed ejection novae. I don't think so far we've managed to observe them. There are some suggestions that some weird X-ray transit that were discovered in the Magellan clouds could be these failed ejected novae, because then you get X-ray emission from the nuclear burning on the white dwarf, but they don't really bright optical transient. So some of the X-ray transit that were discovered in the Magellan cloud has been suggested to be maybe failed ejected nova, but I think we need more to be able to constrain what they would look like in the optical. So, yeah.
Right. Ms. Elias? Okay, so the final, last but not least thing that goes boom, supernovae from bounce to breakout by David Vartanyan.
Thank you, Sarah. And thank you everyone for making it to the last day. Are we good on Zoom? How's my hair? My name is David Vartanyan, and not to one up Elias, but I do supernovae, namely core collapse supernovae. So supernova theory has had a thorny history spanning over half a century. Our models for over 50 years, or previous models, would fail to explode. They cannot produce these explosions. In the last several years, just happening to coincide with my own PhD work, there was a paradigm shift from a schema where simulation models, these are high performance computing, costly rad hydro simulations, would collectively fail to produce explosions, to now where we are able to not only produce explosions, but produce robust explosions with yields, diagnostics, energies consistent with not only fundamental expectations, but also with observations. You can see one such explosion here. This is done with our rad hydro code Fornax. This is with only neutrinos, neutrino-driven core collapse supernova. So no rotation, no magnetic fields. And this is a 16 solar mass progenitor and explodes as such. You see the entropy profile is the shock with a wingspan of around 10,000 kilometers. So if you take a snapshot, you might see a picture that's familiar to you if you look down on your badges. This is from one of our models. Speaking of, Paul, any word on the royalties I'll be getting for use of this image?
No word yet.
Okay, anything to, maintain my lavish lifestyle as opposed to
Getting a large percentage of the money we get.
So I'll begin as one does with my conclusions. This is again a 25 solar mass star, again exploding. So 3D rad hydro simulations produce explosions with neutrinos alone. We see energy between 0.1 to 2 beta, that's 10 to the 51 ergs. We have nickel yields of up to a 10th of a solar mass, so it's less visible each time. We see a diverse of explosion morphologies. We're able to see black holes form from models between 12 to 15 solar masses. For some reason, other stars do explode. We do not see a red supergiant problem. We see models that are 20, 30, 40 solar masses explode without too much difficulty. We're also able to see spins of around tens of milliseconds for some rare models, kicks over 1,000 kilometers per second. And we're able to see strong convection in the forming neutron star core, which can be fertile grounds for powering, when coupled with rotation and MRI, dynamo-powered magnetic fields. But these are all done without any rotation initially, any B fields initially. So neutrinos alone are able to produce the garden variety core collapse supernova we see. So just to convince you, stars explode. On the left, on the right, I apologize, we plot energies and black dots from our various simulations, overplotted observations in color with error bars. And across a distribution of ejecta masses, we're able to reproduce the distribution of explosion energies, again, from less than 0.1 beta to up to several 2 beta, 10 to the 51 ergs. And in some cases, not infrequently, we see neutron star masses left behind that are above 2.1 solar masses in baryonic matter. So that's great, but these explosions are costly. We've used maybe upwards of just shy of 1 billion CPU hours in various HPCs around the US, and we've contributed non-negligibly to global warming in that sense. So taking a step back, there's an interesting question that arises. How can we predict ab initio without any model which stars exploded? And you can by eye, you can with a machine learning algorithm, you can with an analytical or semi-analytical approach, you can estimate around 90% accuracy initially which stars explode without running any simulation. And how do you do that? So if you look at the top right panel, I plot the density versus the enclosed mass for initial conditions for a variety of models, from 9 to 60 solar masses. So this is just the density. It has not been involved. It's what we get from our Kepler or MESA affiliates who share with us their 1D initial stellar evolution models before core collapse, at the onset of core collapse. And if you see, some of these models have a sharp density drop between 1.5 to 2 solar masses, where the density at around a few million grams per cc drops by a factor of 2 to 3. This corresponds to silicon-oxygen interface. Interior to this, imagine you're a shock. You had 1 solar mass, just outside your initial Chandrasekhar mass. The core has bounced, it's driven this fledgling shock, and you're there. And you see matter at high densities falling past you. These high densities power a high accretion of neutron luminosity behind the shock. As matter continues to fall, all of a sudden you encounter the silicon-oxygen interface, where the density is dropped by a factor of 3, and so the ramp pressure also drops quite significantly. And so behind you, you have this high accretion-powered neutron luminosity. Ahead of you, you see a region of low ramp pressure. And this combination provides a fertile breeding ground for a successful revival of these stalled shocks. And so using this two-parameter approach, where is the silicon-oxygen interface in mass, and how deep is it, we can find with 90% accuracy which models exploded. And this is important because we can first predict which models can explode and verify that with our simulations. And secondly, it also emphasizes that many of the other parameterized methods of determining which stars explode perform poorly. And so if you use other estimates, I implore you to consider using this simple two-parameter approach, which gives you quite good accuracy. And this is just the first step. This is just to classify, does a star explode or not? It's a binary. We can go beyond. And so some future but more challenging efforts will focus on seeing if you can quantify what the yields will be. Given an initial condition, without running a simulation, what will the nickel yields be? Can we estimate the explosion energies will be? And I think that's an interesting opportunity for future work. But now back to global warming, we've now run tens of 3D models out to from 2 to 6 seconds. And no matter what anyone tells you, 6 seconds is a long time for rad hydro simulations. This has been, in the last decade, we can do maybe half a second, would improve the access to HPCs, better software. We can now run these out for later times. And it's important to see what happens at late times because it takes many seconds for the quantities, like the explosion energy, to asymptote. And so this is a various collage of our different 3D models from 9 to 60 solar masses. You see small plumes, large plumes, plumes of all sizes. They're very asymmetric. And so I show here a snapshot of our last simulation, last generation. We have newer ones that are now not yet in print. Every movie you'll see here explodes except one, and I'll let you guess which star here does not explode. These are all entropy profiles lasting from half a second to around a second. You see 9 on the top, down to 60 solar masses on the bottom right. So feel free to just guess which model here does not explode. 13. I hear 13. That's a good guess, Melinda. That's correct. In fact, we see for some reason stars between 12 to 15 solar masses do not explode. And this may be verified through gaps in the neutron star distribution because stars in this mass range would partition from black holes, not neutron stars. So that's one possible interest. But we don't have to have this dichotomy between supernovae and black holes. It's possible in some cases to form both a supernova and a coincident black hole. Why? Because these explosions are so asymmetric. Here we show a 40 solar mass black hole. This forms a robust explosion, 1.5 beta. That's 1.5 times 10 to the 51 ergs of energy. It explodes along the northwest hemisphere, but it continues to accrete in this 5 o'clock shadow. So at 1.5 seconds, you have a robust explosion, and then you collapse to a black hole. And this black hole powers, as you see on the left, a jet with a disk. The disk is rapidly rotating with an A of around 0.1 gm over c squared. If you form it instead of a disk and a black hole, it collapses to a neutron star, you would have angular momentum that would provide spins of 3 milliseconds for the forming neutron star. For a model that does not have any initial rotation, it's powered by neutrinos alone, you end up with some coherent accretion that can power these high spins, produce high jets, and produce kicks in rare cases that are above 1100 kilometers per second. And at 6 seconds or so past core bounds, you still have continued accretion onto the remnant object. So that's enough theory. What can we observe? Namely, 2 things. We can see gravitational waves and neutrinos. Core collapse supernovae have quadrupolar time-dependent asymmetries in both the matter motions as well as the neutrino fluctuations. And so you can get gravitational waves powered by both matter and neutrino asymmetries. We plot here on the left column a black hole former, on the right an exploding model, and we show the spectrograms on the top row for gravitational wave energy and the bottom for strains. The energy is a function of strain times frequency squared. So the top row emphasizes higher frequency components and the bottom row lower frequency components. And there's a lot to discuss here, but the important point is you see a dominant F mode frequency on the top right panel with a flare of bandwidth, which is 8,000 hertz. This is powered by accretion, turbulent accretion onto a neutron star that excites astrocosmological motions that you see as this F mode and high frequency motions. You have here the entropy profile where you see accretion fingers, tendrils probe into the deep core and excite oscillations of the core, which we see as F modes and high frequency, in some cases, P modes. And so these are detectable. On the right, I show the amplitude spectrograms for models from 9 to 23 solar masses overplotted with the sensitivity curves for various detectors from Einstein telescope to DESIGO to LIGO. And for a galactic event at 10 kiloparsecs, we can see a distribution of events. If we have a 40 solar mass progenitor that forms a black hole with high spins and has a jet, we can see the strain out to maybe 50 kiloparsecs. If it's a rapidly rotating jet powered model, we can see it out to Andromeda out to a mid-parsec. And you can hear those. These are in the kilohertz range. That's for a non-rotating model. This is for a rotating model. You can hear a chirp for the rotating case at bounce because of an oblate correlated oscillating core. So just add here, briefly add that we can also see neutrinos. On the right, I plot the neutrino luminosity half-life as a function of core compactness, which is just the mass over the radius of the core. And you see what seems to be a Phillips-like relation for type 2 core collapse supernovae. More massive, more compact objects have a longer duration luminosity plateaus. All of our data is public on my website. You can see it down there as simple ASCII text files. So when it comes to a conclusion here, this is my current and ongoing work. In the current generation of new and upcoming supernova surveys, there will be an unfortunate increase in supernova detections. Unfortunate because our models cannot keep up with them. There will be a growing gap between what we see and what we can observe. And so I have a modest proposal. I've developed this pipeline with collaborators on the top right. This is an extensive project. It takes an initial model from Kepler, MESA, whatever 1 year 3D conditions you have, and evolves it as a core collapse supernova, carries it out from 6 seconds until shock breakout at hours to days, and then feeds it a nuclear network and pipes that into Sedona or any other light curve of spectral processing code. And so for any given initial star, a 10, a 20 star mass, what have you, you can then get a supernova outburst, you can get the morphologies, the nickel yields, light curve spectra, energies, distributions of the ejecta. And one example that we've done, this is just, you can see the date on the bottom right figure, it's done this week. We've taken our 23 solar mass 3D progenitor, evolved it through this pipeline. We have now coupled 6 seconds, 10,000 kilometer shocks to 200,000 seconds, so over 3 days, to just shy of a billion kilometers in radius. And you see an interesting radiator instabilities form as the shock propagates a hydrogen helium interface. You see a reverse shock forming that interacts with the outmoving ejecta. On the bottom right, you see 500 million kilometer scale nickel plumes that show this interesting tripolar structure. It's very possible that the asymmetry of the ejecta at days is coupled to the asymmetry of the supernova at second time scale. So you're able to couple these vastly different physical length, time, and astronomical scales through this network. And so we made a lot of progress in core collapse. The problem is not yet done. I think the work we have ahead of us is clear cut. We know what to do. So I'll conclude these pithy remarks. The supernova problem is solved. Long live the supernova problem. Thank you.
Hi, Joe on Hawaii. I want to ask you about the discussion of keywords. Specifically, I would like to get your comments on how one would identify the keywords, that is, to assign to those keywords which are observed, identifications of which was computed from the stellar, and also about driving mechanism for these keywords in the project database, which is obviously one we would have to use in order to, use these keywords to constrain the structure and the project database.
Good question. So the idea is how can we identify P modes from observations and how can we constrain the general properties from those? So P modes or pressure modes. The easiest way you have templates. You can then do model decomposition on your templates and on your observations, and you look for frequency patterns. So the P modes may be harmonics of lower modes like the F mode, because the F mode is really the boundary between the G mode and the P mode. So you can do a frequency decomposition, see if these are frequencies you'd expect, and you can then classify F0 and then P1, P2, and so forth. And as for the progenitor, that's a bit of a tougher question because the combination of F, P, and G modes are evanescent because the convective core sort of just squashes these features, all probe different features. So the F mode probes the accretion onto the PNS and the PNS properties. P modes would probe in the supernova phase the accretion dynamics on larger scales. And if you see lower frequency motions down to 20 hertz or so, you'd see large scale ejecta features. That's sort of the rough distribution between what a P, F, and G mode would tell you.
Hey, great talk, thanks. So rewinding back to this sort of paradigm shift you mentioned from models not exploding to models exploding robustly, was it just kind of a sort of eureka moment where people figured out this one essential thing, or was it a lot of little things?
That's a good question. So there were three key effects that affected this transition from non-explosion to explosion, and they are in no order of importance. First, improved access to HPCs. There are more computers we could use to do more models, and also improved software. We can now simulate the rad hydro more efficiently and more accurately. Second, we had a better understanding of what the initial conditions were. We had more Mason Kepler models. We could identify key features and explore them like this look and option interface. And thirdly, we also had an improved understanding of the neutrino microphysics that are so key to this. So that would be a eureka moment. There's this sort of idea of here's one effect, the many body effect that affects the neutrino nucleon scattering cross section that has a quantitative effect of a few percent, then transitions black holes or what it does to exploding supernovae. So the combination of those three effects, I'd say, is what caused this transition.
All right, let's thank David and all the great speakers.